All right, so I think we can go ahead and get started. Hi, everyone. My name is Nathan Piccini. I am one of the marketing managers at Data Science Dojo. And Dan, um, I should have stopped by. You're right. But today I have Roberto Cadilli with me. He is a data scientist at KNIME, and he's going to be going through a friendly introduction to Codeless Deep Learning with us. Just a couple of things for today. For Q&A, we are going to be answering questions kind of intermittently, as long as they don't take a ton of time to answer. And then for those questions that do take a little longer, we're going to save them for the end. There will be a live demo of the platform at the end, so make sure to stick around for that. And we're going to try and make sure we have enough time to go through the full demo and we don't have to cut anything short. And then if you are on one of our live streams, LinkedIn, Facebook, Twitter, YouTube, anywhere else, go ahead and answer your questions, or well, answer your questions, but ask your questions, and we'll make sure to bring them into Zoom so that we can make sure to answer those as well. If you are on Zoom, please use the Q&A tab for questions. It just helps us keep everything organized, because sometimes the chat can get a little crazy and we end up losing things. So with that, Roberto, why don't you go on ahead? I'm going to keep dreaming about Minneapolis and fishing on Leech Lake, and you can start telling us about Codeless Deep Learning.
Thank you very much, Nathan, and welcome everybody to this friendly introduction to Codeless Deep Learning with KNIME Analytics Platform. And so I think it's right about time to start. So before starting, maybe just a few words about myself. I'm a data scientist on the evangelism team in KNIME, and I have a strong interest in machine learning and algorithms and deep learning architectures, especially for NLP and computer vision. And you can get in touch with me on LinkedIn, on Twitter, or by email. I already see there is a question in the Q&A about somebody asking about this slide. This will be provided to you in the follow-up email. So thank you, Nathan and Fatima, for taking care of that. So don't worry about that. And I think enough about myself. Let's get started. And maybe the first question we need to try to answer is, what is deep learning? So as you can see from the slide already, deep learning is just a smaller part of a much broader domain of artificial intelligence. And by artificial intelligence, which we mean any technique that basically enables machine to mimic the intelligence and behavior of a human being. And as you can see from the slide, we have then deeper levels, where the next level would be machine learning. And in machine learning, we try to let a computer or a model learn without being explicitly programmed to do that, by just relying on using past observation. So learning from the past to predict, or to spit some predictions about the future. And within the realm of machine learning, then we have neural networks, which are popular, and actually they're not let's say they're not new algorithms. They've already been around since the 50s, but often not being used until, let's say, relatively recent times, because of the computational power that was not basic enough. So they actually been around for a long time, but their use and their widespread is connected to the possibility to have now much more powerful machines. And within the realm of neural networks, finally we find deep learning, which is basically a modern evolution of neural networks. They are deeper, so they can be used for much more complicated tasks. We have a wide variety of architectures there, and we will see, for example, convolutional neural networks later on in this webinar today. So, but let's get first an idea, a basic idea behind neural networks and deep learning. So, as I mentioned already, we need to start simple, first of all. As I mentioned already, the artificial neuron per se, and neural networks per se, they are already been around since the 50s, but they are, in their existence, let's say their creation stems from what is a biological neuron. So as you can see here in the slide, we have a simple neuron where we have some input information. being received by the dendrites, and which are these extremities here. And these inputs are passed to a cell body. And whenever the cell body fires, we have a signal that is being passed on toward throughout the axon. And finally, this produces some outputs. So based on the idea of a biological neuron, researchers have tried to emulate this by creating what is called an artificial neuron or a perceptron. And as you can see in a perceptron, what we do have still, again, some inputs. We then have some weights, which in a way try to tell us what the information from the inputs is more important for the network to learn. And then we usually had a bias term, and we input all this information into another neuron here. And this neuron then will produce an output. So normally what we do, as you can see here on the slide, we do a weighted sum of the inputs and the weights, and we had a bias term. And this information is passed on to a neuron, and we wrap, let's say, this information into an activation function. And this activation function, depending what activation function we're using, for example, let's imagine we're using a sigmoid activation function. The output of a sigmoid activation function can be interpreted as a probability, and therefore our output can be, as a result, interpreted as a probability. And that's actually one of the reasons why sigmoid is often used, because it's convenient for interpretation. However, a simple perceptron is not very powerful. It's not able, let's say, to deal with problems where data are not linearly separable, for example. And so we can increase the complexity of our artificial neuron, our simple artificial neuron, to create and to emulate actually what happens in nature, in our brain, by creating a network of neurons. And in the same way, our brain functions using multiple neurons that are connected by creating a network. We can have artificial neurons then try to mimic a little bit that structure. And so in this case, as you can see here, we would have multiple input, so in an input layer, that are fully connected to the neurons that comes next in these two hidden layers. And these neurons in the hidden layers are also fully connected to the neurons in the next hidden layer. And always here, as you can see, we have a weighted sum, an activation function that helps the network. That helps the neuron fires an output. And this output that, for example, is being fired here is then used as the input and multiply with the weight for the next neuron, until we obviously produce some output. And this, as you can see here, is a very common network topology being called fully connected feed-forward neural network. As I said already, we often have different activation functions. A popular one is, for example, the sigmoid, and it's popular mostly because the output can be interpreted as a probability. And the sigmoid is usually used whenever we have a binary classification problem, so just two classes, and it's bounded, as you can see from the slide, between value of 0 and 1. Another popular activation function that is usually used in hidden layers of neural networks is the tanh. And here this function is bounded between -1 and 1. And it is often used in hidden layers, so within the structure of the network, because it helps. It is a function that helps convergence, and it helps the model converge faster than for example, the sigmoid. And finally, we also have a very popular, and more recent, let's say, but still in a very popular activation function, which is ReLU. And this is, for example, so this is defined between 0. So for all negative inputs, it will return a value of 0, and otherwise it will return the value itself. And this is often used it's very popular nowadays, and is often used, for example, in convolutional neural networks. And we will see that later on. And I want now to give you a small example. Imagine we have some data that we collect some data about people taking the L1 certification, the KNIME L1 certification, and some people, of course, have passed the certification, and some they don't. And we have just two input features. That is to say, the minutes they have attended the course and the workflows they have built in that time. And so we can then create a simple feed-forward neural network. As you can see here, we have an input layer with our inputs, the minutes of course attended, and the workflows built. We connect this inputs, so the input neurons here in an input layer, with the neurons in our hidden layer. And we have, as you can see here, some randomly initialized weights. And we have a Bayes term as usual. And as you can see here, also we are using in the hidden layer a tanh function. The same happens afterwards. And again, here on the other hand, we use a sigmoid function in the output layer because, as I said, it provides an output that is easier to interpret. And so we decide that whenever the probability, so we basically want to do a classification task. We want to predict whether a person has passed the exam or not passed the classification exam. So whenever the output is above or equal to 0.5, then we will classify as passed. And whenever it's below 0.5, then it will be classified as failed. Okay, so now we have our data set, and then we want to apply our network that we built to a new sample. So this new sample is indicated by this red cross. And as you can see from, let's say, from an exploratory analysis of our data in this scatter plot, this person has attended many minutes of courses, and he also has built many different workflows. So our expectation, let's say, having attended 170 minutes of course and having built 8 workflows, is that this person should probably pass the exam. Okay, let's see what happened. So we have our network, we provide our input, we normalize them, we let the input data flow into our network, and we produce an output. But as you can see, the output that is being returned is rather below 0.5, which will then mean that the person would be classified as failed. And the reason why the network at this moment is not producing the output that we would expect is because we didn't train the network. We just provide the input. We just had randomly initialized weights. There was no training. We just used the current weights and provide an output for that. So there was no learning process for that. So how can we then train a simple neural network? So training a neural network means, in general, finding the good weights to produce the output that, well, in this case, we would expect, for example, a pass, right? So we need to, of course, introduce the concept of predicted value. In this case, was 0.013, and the true value in this case would have been value of 1. But we also need to let the network know that it's making a mistake. So we need to introduce the concept of errors. So we need the network to be aware when it's making a mistake. And this is usually done by introducing the concept of a loss function. So, and as you can see here in the lower part, we have a loss function, and the predicted value is defined by the inputs that we have here and the metrics or weights. And of course, we compute this loss, this error by, let's say, in a very generic way, by compute the difference between our predicted value and our true value. Obviously, this is more complicated. For example, we can use a binary cross entropy in case we are in a binary classification problem. But we don't simply want to use or to calculate the error for just one training sample, like the one we have here, 170 minutes and 8 workflows. But we need to calculate this for all training samples in our training set. So we need to basically provide a sum. So we need to have a loss function that is a function of the weights, so the metrics of weights, that is basically equal to the sum of those errors. All right, so we now have given the network a way to recognize when it's making a mistake. But how do we actually train the network to find good weights? And that's something that we're gonna see in a moment. Before that, let me just show you in this slide how the loss landscape looks like. So as we already said, the goal of the training is to find the W1, W2, so our weights that reach so that we can reach our global minimum in the loss landscape. So in this case, obviously we have only two weights, so it's easy to represent in this way. But normally when we have hundreds of different weights, it's not so easy to represent. And what we want to do is we need to update, we need to train the network so that it learns how to return those weights properly. And how can we do that? This is let's say the idea behind gradient descent. The gradient descent is a popular optimization algorithm used in neural networks. And I will try to first introduce it with an analogy of a mountaineer cycling in foggy condition. So imagine you are on top of a mountain, like in the slide you saw before, right? You are on top of the mountain there, and that's your current position. So you start at your current position, and what you want to do is that you are in foggy conditions, so you don't know what's happening. So you don't know how to proceed downwards because you don't know what downwards is. So what you need to do is to look basically for the direction of the steepest ascent. So if you know that what is the steepest ascent, you know that taking a step in the opposite direction will lead you to the bottom of the valley. And so we repeat this process multiple times iteratively until we reach the bottom of the valley and we return the position. So and that would be basically returning the value of the weights. So now, whether we conclude with this analogy, we can see actually how, in a more, let's say, more precise way, how the gradient descent algorithm works. So again, we start with the initial position, which is basically with the randomly initialized weights. And what we do is we need to enter a procedure that will be repeated iteratively until we reach a minimum of a given cost function. And so we calculate first the gradient with respect to the weight. So remember, when we do so, we basically calculate the partial derivatives of the loss function with respect to the weights. In this case, we had just weight W1 and W2. And then we make then a little step in the opposite direction, so towards the descendant, right? So we calculate first the ascent, and then we take a step in the opposite direction. And we repeat this process many times by updating the weights until we reach the bottom of the valley where we have the minimum value of the given cost function, and where we then return the weights that are then be used by our networks to produce a much more meaningful prediction. Okay, so if you want to visualize this, imagine then we have again our let's say our loss landscape. We have the weights 1 and weight 2. We take the partial derivatives of the loss function with respect to the weights, and so we first calculate the steepest ascent, so the gradient of the cost function, and then we take a step in the opposite direction. And then we keep doing this and step by step. Obviously, the size of the step is something that is being also it's also let's say a hyperparameter that we can choose, and it's called the learning rate. So by how much we decide to take the step, but we repeat the process multiple times until we finally reach the minimum or the global minimum of our loss function, and then we return these weights. And an efficient way to calculate the gradient during this optimization process is towards the concept of back-propagation. So we usually have what is called a forward pass, where we use the current weights. And so this is something we already seen before. So we have the inputs, we multiply them by the weights, we obtain an intermediate here output, which then becomes the input that is being multiplied again towards some new weights and to produce an output. And here, then we calculate finally the error. In the backward pass, so that is the most important, let's say, point here, is that we basically propagate the error. So we calculate the error and we propagate it towards our network so that the weights can be then updated. So the model can learn and the weights can be updated. And we do so by a process of derivation, as I said before. And mathematically speaking, this is what is called a chain rule in derivation. And for example, if we want to take the derivative of the loss function with respect to W2, we would then take the derivative of the loss function with respect to our prediction, and we multiply it by the derivative of our prediction with respect to W2. So we would then be here. And then we can do the same, right, for the other weights, for the W1. So it's a similar procedure. And for example, this term is exactly the same, so it can be taken exactly as it was computed here. But we do introduce a new let's say term here. So the derivative of our output with respect to our intermediate output. So this is say the output of our intermediate, so our neurons in our hidden layers, and then again the derivative of our intermediate output with respect to W1. And so with this process, we can then basically train our model and make it and change those weights so that they actually minimize our loss. And so now, if we try to do the same procedure, you will see that we start again with this our inputs. We normalize them. We leave the data. Now we have trained our model, and therefore, as you can see, the output is way above 0.5, indicating a passing. But consider that what I show you just right now, it's in the loss landscape especially, is just a simplification. In real neural networks, we have many different weights, hundreds of weights, or even, well, millions, depending on which architecture we're using. And therefore, it's not so easy to represent a loss landscape. Here I've taken a screenshot from the paper that you see here in the slide, where they've done some dimensionality reduction to be able to plot a little bit the loss landscape. And as you can see, there are potentially many local minimum, but we want to find the global minimum of our loss landscape. And so an important part in this learning process in the gradient descent algorithm is, as I said before, is the learning rate. So by how much, so how long the length of our step, let's say, toward the global minimum. But let's say we have different types of learning rates. We have learning rate schedules that are usually something that we need to manually define, or that require, let's say, the definition after each iteration or epochs. But we also have many different optimizers that are adaptive optimizer, for example, Adam, Adagrad, and so on. And they basically so they usually use a different learning rate for each parameter, for each weight in our model. So the learning process is much faster and also much better, because it takes usually bigger steps in the beginning, and then as the model, that's right, reaches or is about to reach convergence, we take then slower steps so that we avoid, let's say, jumping over the global minimum, and so we don't miss it. Other important elements in the way we train our neural network is, for example, the choice of a batch size. That is to say, which is basically defined by the number of samples that we use for each update. Consider that, for example, training a neural network with all the entire training set at once can be very expensive, computationally very expensive. So what we usually do is we basically do some batch size training. So we take just a batch, so a sample, and we basically compute the gradient descent on them, and then we take another batch, and so on. And another important, let's say, other parameter that we can choose is the number of epochs. So basically, how often each sample is being used during our training. And this obviously, usually, if we increase the number of epochs, we tend to have better performance. But let's say at the cost of extending or stretching the training time, and then of course is something maybe we need to consider as well. Before moving to our next topics, I would like to show you a few important, let's say, things that you can keep in mind when setting a feed-forward neural network. For example, you can think of how many layers you want to introduce, and for each layer, for example, how many neurons you want to have, which activation function to use, and which loss function, for example, also to use, and is there any optimizer we need? So there is many different factors that influence the performance of the network, besides obviously the training process where we need to update the weight. And with that, I would like to show you very shortly a small demo in KNIME Analytics Platform on how to build a fully connected feed-forward neural network. The example is the same of the one we had in the slide. So we have here a CSV reader where we have certification results. So if I open the table, so you have the number of workflows that were built, the numbers of minutes that were attended, and this is the class, so either passed or not passed. So this is something that, of course, so this is obviously a supervised approach. So we need to have labels. And what we do very simply, we first encode our target class. So we encode it so that whenever it's passed, it's a 1. Whenever it's not a pass, it's a 0. So very simply. And then we basically partition our data set into training, 70%, and 30% is going to be given to test verification. So sorry, validation and test. So and so as you can see here, then we would have 10% for validation and 90% for a test. And in between, we normalize, of course, our input features. So how do we start building our simple neural network? So the first thing we need to do is, of course, install the KNIME Keras Integration that obviously allows you to then use the Keras nodes. And in much same way you would, for example, in traditional scripting language, like for example Python, you would simply call a specific layer. So here we need to start with an input layer. So we just type in the node repository, Keras input layer. So we drag and drop it from the node repository onto our workbench, and we double click to configure it. So the most important part here is really to determine the shape of our input. So we have two variables. So we have basically the minutes of course attended and the number of workflow built. So here the input is obviously going to be 2. And then we click OK, and we can execute it by right click and say execute. Right. We then want to have, as I said, a fully connected feed-forward neural network. So to have that, we need to have a so-called dense layer. So we start with a Keras dense layer. We write it down, we type it, and we drag and drop it again. We connect the two nodes. So we have 2. Of course, we need to configure it. How do we do it? So first of all, here when we need to, so we have the inputs, that's the input tensor that comes of course from our Keras input layer, and in the units configuration, we need to determine how many neurons we would like to have in this first in this layer. And let's say we want to have, for example, I don't know, 4 units, and then we need to choose the activation function. Just to mimic what I did in the slides, I'm going to choose a TANH. So we have many different ones, as you can see, a TANH. And then we're going to go OK and execute it. You can also do with F7 for a shortcut. And then I want to have another hidden layer, which is also, so sorry, this was the first layer that I want to have the last output layer. So, and then for that, I can drag and drop another Keras dense layer. I also connected, and here I need to provide two important things again: the number of units. In this case, because it's going to be a binary classification problem, it's enough just to have one output neuron, because the value that it's going to give us is going to be we're going to be able to interpret as a probability, given that we use here in this case a sigmoid activation function. And I also want to give a different name here. So we just call it output. So it's going to be clear for later on what that this is going to be an output, the output layer. So I'm going to go OK. And so here we have basically built we have basically defined our network structure. What we need to do next is to basically use a Keras learner node. Sorry. Keras network learner node, because this node will be responsible for basically the learning process. So what we do here is we connect the network architecture. We provide the training set here, and we provide the validation set. And here we have to configure it, of course, and we double click. So as input data, we only want our input feature, so we remove this one. In our target data tab, we only want, in this case, just the encoder class. And we already have, in this case, a binary cross entropy as a loss function, which is fine for this case. And then we have some options here, option tab, where, for example, we can choose whether we want to shuffle the training data before each epoch, how many epochs we want to have. And for example, I don't know, we can have maybe 120, I don't know, something like this. And we can also choose our optimizer. We have different optimizer we can choose from. And for this case, I don't know, let's go for Adam. This is just an example. You can obviously engage in a hyperparameter optimization process with the dedicated nodes that we have, and then obviously find which one would perform better. And at this point, we are ready to start our training process. So I simply execute that. In a moment, it will start. Bear with me. All right. And the funny thing is, interesting thing is, we can monitor the learning process by opening the view. And we have here different tabs. We can monitor the accuracy, where you see the red line indicate the training data, whereas the blue line indicates the validation data. We have obviously also the option to see what's happening in the validation. But we also can see what's happening in the loss tab, and how the loss is decreasing over each epoch. And just for matter of time, I would stop the learning here, and I will show you then how to continue with the workflow. I already prepared it here. So we are at this point where we have finally trained our model, and it's completely trained. And we then basically use this trained model to finally use it on new unseen data, which is the bottom here is the test. And we can let's say apply this model using the Keras network executor node. And if I just click in here, you can see we had defined an input batch at 100. We have obviously the input features again, the same one that we had before. And as our output, we would have, of course, this output sigmoid 0. That the output is basically the name of the output layer that we provide at the beginning. We can then do some calculation here. So you see, by the way, the output is being returned. It can be interpreted as a probability, and since we use a sigmoid activation function, and we're using a simple rule engine node, we can determine the threshold, and finally we can inspect our performance, for example, with the scorer node. And you see, with just a simple network like this, we already reach a 92% accuracy. Okay, and on that, maybe before we continue, I will check quickly the Q&A. To see if there is any question. Yes, of course. So there is somebody asking about whether it's possible to create a fraud detection model in deep learning. Sure. And we have actually, if you go to the KNIME Hub, it's the KNIME repository for workflows and nodes and components, which is all free. There are many, actually, examples of fraud detection using deep learning. What we can do is, if you go to the KNIME Hub, it's the KNIME repository for workflows and nodes and components, which is all free. There are many, actually, examples of fraud detection using deep learning. There are many, actually, examples of fraud detection using deep learning. There is then a question by Marcus, who was asking, the test set is really separated from model creation. I'm not sure exactly what you mean, separated from the model creation. So the test set is being created here when we partition our training data, and we pay attention that we also normalize the test set using this apply node. So we do it actually after partitioning, so that we avoid any data leakage problem. And then, of course, we then have here another partitioning node where we we will basically create a validation set and a test set. Yeah, that's another question. Maybe I can about entering the field of deep learning. Maybe we can leave it to the end, so there is more discussion. And with that, I would like to go back to the slides, and this is the model that I just showed you, and then move from a simple neural network. So when do neural networks become deep neural networks? That's a very actually not a simple question to answer, because is it the number of hidden layers? Usually yes, but it's also maybe the task that you can finally solve with deep architectures, which may be another parameter that defines what a deep architecture, deep learning can be, or deep neural network can be. So it can be the number of hidden layers that you have, the number of neurons in each hidden layer, but also the architecture itself. But the thing is, the most important thing is, which probably is the most remarkable, as I kind of already mentioned a little bit, is the fact that creating or working or using in general deep neural networks helps in the solving tasks that are not possible, that are not easy to solve with traditional machine learning models. For example, let's say convolutional neural network, for example, for image classification or image segmentation, or recurrent neural networks for let's say sentiment analysis, so for language modeling in general, or other architecture, for example, transformers, which is on the architecture on which BERT is based on, and so on. So there are, let's say, different let's say ideas on what defines a deep neural network, but most probably the best way to explain it is the task that you can, and the complexity of the problem you can solve. And I want to now move to a new realm that is of computer vision, and with a very simple task of classification. Maybe if you're not familiar with the idea of computer vision, the idea of computer vision in general is to basically automate some tasks that could be performed by our vision system as humans. But imagine you have thousands of different data of images or video fragments. You don't want to do this on your own, so you want to automate this process, and you have to do that. You need to have a neural network, and actually a deep neural network, in fact. And so I want to show you here how you can solve the task of image classification. MNIST image classification is a popular data set where we need to classify handwritten digits between 0 and 9. And to do that, we need to first understand how machine can represent images, right? So in the case of our data set, they are grayscale images, so like in the slides here. So normally what we do is that grayscale images can be represented as can be stored and represented as a matrix where each pixel corresponds to a value. So each cell represents one pixel of the image, and it is associated to one value. As you can see, for example, whenever we have a black pixel, we will have a value of 0. And whenever we have a white pixel, we have a value of 1. And whenever we have a gray pixel, then we have a value of 0.5. But usually, so although in this specific case, we're going to work with grayscale images, usually we tend to work with color images. So images that have colors, and this can be also used. This can also be represented, and this can be represented by encoding, let's say, the color image by different channels. So for example, for the reds, for the greens, for the blues, we can have different channels. So we basically then end up with a tensor where each channel represents one color. All right, so now that we know how machines our machine sees images, basically a numerical representation of them, we need to ask how we can identify different features in those images. So, for example, we could use the idea of filters to check for different feature in image patches. So, as you can see here, for example, we have an underlying cross that is represented by this white pixel 1, and we have been using different let's say filters here to identify this part of the cross, so the upper arm, the upper left arm of the cross, or this other filter to identify, let's say, the central part of the cross. But obviously, as you can imagine, creating the value, so manually crafting those filters is extremely hard. You need to have, of course, domain knowledge, but it's just simply a computationally expensive and time-consuming task. So how can we do that in a way? How can we apply a filter in a way that is being automatically, so the values in it that are needed to extract the features from our image can be automatically learned? So the idea of applying a filter in a much more interesting way is that whenever we have a high value, when the filter returns a high value, we would have, so the feature is in the image patch. Whenever we have a low value, then the feature is not in the image patch. And the idea is, in a similar way of what I mentioned in the previous slide, is to use a matrix or a filter or a kernel, which is there are synonyms in these cases, and place it on top of the image and basically slide that kernel across the image and computing some multiplication, basically multiplying the pixel value with the value contained in the matrix. And I'll show you how you can do this. So imagine we have this specific filter. We move it across our image. We slide across our image. We do an element-wise multiplication. So we multiply the 1 in the matrix here and in the filter with the value here. And we then sum this multiplication until we obtain, for example, a value of 9, which is pretty high. And you will see this filter, the filter yellow, was exactly were especially fit to extract this part of our let's say arm in our cross. But using the same filter in this area would have not yielded the same result. In fact, if we use exactly the same filter here in this lower arm of our X, we will end up with a low value, which indicates the absence of the feature in the image patch. Obviously, we can stack many different filters, but we want to have this process in a way that is automated. So we want to learn the values in the filter in an automated way. And by the way, this is what constitutes the fundamental of a convolutional operation. And that's exactly what brings us to the idea of convolutional neural networks. So a convolutional neural network is a network that has at least one convolutional layer. And in this convolutional layer, we have those filters. And instead of crafting different features or different filter to capture those features, a convolutional neural network, what it does, it basically learns features in a hierarchical way. So that, for example, we can extract low-level features at the beginning, which basically usually correspond to some edges, some spots. We then use the feature learn, so the low-level feature learn, to extract mid-level features. In this case, could be, for example, some ears, some nose, or some eyes. And then again, use this mid-level feature to learn and to extract high-level feature. In this case, would be, for example, a complete facial structure. And as I mentioned already before, the idea of how the convolutional layer work is basically to slide this matrix of weights across the image and to do an element-wise multiplication and then summing this multiplication to produce a specific value. And the next slide, you will see that how this can be done. So the idea of this weights in this filter is very similar to what we explained in the process of learning the weight in the fully connected feed-forward neural network that we saw at the beginning. So we basically slide the matrix, the filter, on top of our image. And when we do so, as you can see, the slide now changes to weights. We produce some specific values. we pass this value into a ReLU activation function, and we produce, if I go back, a new matrix of values, where we have, as you can see, and whenever we have a high value, it would mean that we have a feature. We have a feature there, and in a way, this process is very similar to the way a feed-forward neural network learns, but just in a different it's like this is different architecture. And those weights, that's the most important part, are learned during the training. That's the crucial part, because we don't want to handcraft the values in that filter by hand. It's time consuming. We need to be domain experts to do so, and it's not possible most of the time. There are three more elements that we need to take into account in a convolutional neural network, which is, for example, the stride. And by stride, we mean how many by how many pixels we slide our kernel, our metrics. So in this case, for example, if we have a stride of 2 by 2, we move our metrics, our filter, by 2 pixels each time. We also may want to include a dilation rate. So as you can see in this part, we have usually contiguous kernels, but it's also possible not to have such a situation. And so we can introduce some spaces, so we don't capture the information here, but we capture every other pixel. In this case, this is a dilation. So this is called dilation, and the dilation rate basically controls that information. And we also can introduce sometimes some padding. And padding is something that is especially useful. And by padding, I mean usually zero padding. There is, say, putting, as you can see here from the slide, a series of zeros around the image, so that basically we artificially increase the input of the image, or at the boundary of the image. And this is done usually to make sure that the information, the feature that are at the edges of our image are as frequently captured as those there are in the middle of the image, so that we don't miss some information. But in all those cases, however, in all these two cases, however, whenever we apply a stride or dilation rate, we tend to reduce the spatial resolution of our image. So that's something very important, and that's something that when we decide the values of those hyperparameters, we may want to keep into account. And finally, another important part of a convolutional neural network is the existence of pooling layers. Here, the idea is to basically replace the area of an image or a feature map with some summary statistics. And so we usually need to define the area we want to take into account, for example, a 2 by 2 area. And we then decide to apply some summary statistics. For example, it could be max pooling. So we pick the maximum value of the area we are taking into account, or average pooling, when we take the average value of the area we take into account. The important part here is that we don't have any learning here. There's no any learning happening, but it is extremely important to use pooling layers, because it reduces the spatial resolution between convolutional layers. And with the output with the consequence of reducing computational complexity for our networks, which is obviously something that we want, and also it keeps the most important feature in the network for the network to further learn. And so with this information, we can then finally visualize the full convolutional neural network structure. So an input image, we have a first convolutional layer with a ReLU activation function, the first pooling layer, max pooling, average pooling, for example, another convolutional layer, another pooling, and so on. So we can potentially stack many more convolutional layers. So that's actually up to us, and actually up to the task at hand. And then the last part is usually a feed-forward, fully connected feed-forward neural network. And this is the part that we usually use for the actual classification part. So the convolutional layers and the pooling layer are used to learn the features, and the classification part is rather done by a feed-forward, fully connected neural network. And of course, in this case, we have a softmax in case we have, for example, many different classes, not just a binary classification problem. And that's how we can do, for example, we can build a convolutional neural network in KNIME Analytics Platform for the MNIST classification problem. So here we just ingest the data as the training data and the test data. And the upper part, which is probably the most interesting part, we define the network architecture. So first of all, we need, again, a Keras input layer. And here you see we have an input that is 28, which is the number of pixels by 28, which is obviously, I mean, it's a matrix, the image, so 28 by 28, that they are the pixels. And the last value is a 1. It's basically the number of channels. Since these are grayscale, we only have one grayscale images, we only have one channel, so 1 is enough. And so this is our starting point, the input layer. And then we start building our first convolution. And so in the first Keras convolutional layer, we need to set the number of filters. So in this case, for example, we have 32 filters. This can be more, this can be less. It's really up to you and to the task at hand. And we can then define the size of those filters, or canal size. In this case, is a matrix of 3 by 3 with a stride of 1. So basically, we move 1 pixel at a time. We decide to have no padding, but we do have idellation rate. So we skip every second pixel. And we use an activation function, a ReLU activation function. And then after that, we include a max pooling layer. And here, what we need to define, is the pool size. Again, this is an area of 2 by 2, and we decide to have no padding in this case. And again, so we could potentially stack as many convolution layers as we would like to. And at this point here, stop. So we close, let's say, the convolutional part where we extract the features of our images, and then we can use the Keras flattened layers and the Keras dense layer and another dense layer to actually build, as we saw before, a fully connected feed-forward neural network. And that's actually what happens. So we start by first flattening our input. By flattening, so what this node does, what this layer does, is basically stacking on each row of the metrics of value that we have in our representation of the image. Basically stacks each row as one vector, so one on top of the other. So we have a then flattened input. And then we can then start building our fully connected, feed-forward fully connected neural network. And then, as we saw already before in the learner node, in the Keras network learner node, we define that our input, in this case, is the images, of course. In our target data, we have the target. In this case, this is a list data type. Because we have not just one class, but we have obviously different classes. We have 10 classes, in fact. It's from 0 to 9. And we then set the epochs, and the optimizer in this case was eta delta. And doing this process will yield an accuracy of 94%. But can we improve this performance? Well, the most, let's say, straightforward solution to do that could be, for example, to include more convolutional layers. So the network is able to extract more features from our images. So in this case, as you can see, we stacked another convolutional layer. And by doing so, we keep then the rest exactly the same, except we included, for example, a dropout layer. So as a regularization strategy. And as you can see here, the accuracy of our network improved already by 2%. And another alternative to improve the performance of your convolutional network would be, for example, to do transfer learning. And by transfer learning, I mean basically transfer what a previous model has learned on similar data to your problem and task at hand. And this can be done, for example, by just using the weights that the model has learned before to your task at hand, or it can be done, for example, by importing the same and using the same network architecture, or by, for example, freezing all the convolutional layers, let's assume, and just train the top layer. So basically just retrain to your specific to your specific data problem at hand, just the part where we do the classification. So, and the reason why we want to do often transfer learning, especially when we talk about when we're dealing with images or in general in computer vision, is because normally we need our models to be trained on many, many different images, sometimes thousands or even millions. And it is possible, for example, to use the Keras nodes that we have in KNIME, where you can write some Python, just a few lines of Python, and where you can import, for example, a model that has been trained for, I don't know, a ResNet 50 or a VGG 16 or 19, and then use and then start from there to, let's say, take advantage of that already trained model and to basically build the rest of your network for your task at hand. And with that, I would like, I mean, here do I have this? We have the links to the workflow and that we discussed today, that I show you today. And you can, whenever you get the slides, you can of course go on the KNIME Hub and download it for free. And just so as a as a wrap up for the end of our presentation, if you want to stay up to date with what the KNIME community is sharing and doing, we have a publication on Medium, which is called Low Code for Advanced Data Science. There, the community, so it's a publication that is written and by and for the KNIME community. So you're welcome to submit your stories there. And if you want to learn more, however, about Codeless deep learning or in general about Codeless deep learning with KNIME, I recommend the book that was written by Rosaria and Filippo and Catherine Melcher. They are Rosaria is the head of evangelism at KNIME, and so you have the link there. Or if you want, you can attend our introduction to neural networks and deep learning. This is a course stretched across 4 days, so there is time to go in much more details about both the foundations, but also into different architecture. For example, recurrent neural networks, or more details about convolutional neural networks and different applications. So there is obviously more time there to explore this. And with that, I would like to thank you for your attention, and I am now happy to answer questions. And sorry for the delay.
Yeah, Roberto, so while you're reviewing questions, and while people are probably also typing out questions, I'm going to go over our webinars for next week, and then we'll come back to you. All right?
Yeah.
So, and sorry, I'm just going to share my screen really quick because that always helps me. All right, so, and maybe I can, there we go. So for next week, June 15th at noon, we have Ben Jones, the co-founder of Data Literacy, and he's also an affiliate instructor at the University of Washington Foster School of Business, Go Dogs. And he teaches data visualization and storytelling there, but he's going to be giving a talk on read, write, and think data. And in this talk, it's going to be about a new tool-agnostic framework that Ben actually created. And it's all about posing suitable questions, forming hypotheses, and converting raw data into wisdom. I've had a chat with Ben, really cool guy, would definitely suggest attending. So that's on June 15th. And then on June 17th, which I believe is a Friday, also at noon, we have To and Through Data Science with Jimmy Nguyen, who is a senior data scientist at LinkedIn. And so in this talk, Jimmy's going to be going through his journey with data science and going from where he started out in accounting and finance to self-learning, getting a master's, in his highs and lows on his journey to where he is today as a senior data scientist at LinkedIn. So if that is your goal, like if becoming a data scientist is your goal, I would really suggest joining Jimmy's talk. It's super inspirational and kind of cool to see how the path that he took with self-learning and then getting a master's and then joining LinkedIn. So it looks like we do have a couple more questions. So Roberto, I'll hand it back over to you, and then we can get out of here.
Thank you. Yes, so let me address this question. So I will start maybe from the easiest one, which is KNIME Analytics Platform open source? Yes. So it's open source, it's free. So you can just go to our website, knime.com, and just download it for free and start using it right away. So that's the simplest answer. So it's very easy. and it's also open source, and so open source and free are. I'm not sure if you guys are familiar with the distinction, but in general, yes, it's open source. So you can just go there and download it and start using it right away. Then I see somebody is probably asking about extracting data from invoice with using neural networks. Sure. If you have, for example, well, there's probably some preprocessing you need to do there in the first place, but surely you can, for example, maybe thinking of building a recurrent neural network. We have for that LSTM, Keras LSTM layer nodes. Then are usually a good strategy to map languages, because languages is a sequence. So we want to keep the order of the sequence in which they appear. So to keep the context. So probably if you want to maybe, I don't know, extract data or process or, I don't know, define or predict whether an invoice is going to be paid or not, obviously this depends on your task. Modeling your problem with such a neural network could be a good strategy. Or otherwise, just the entire extraction, yes, that can also be done. And with that, if you have, I know, image data in that sense. And then I see, so yes, the normalization is done after splitting after partitioning. And the reason, as I touched upon like very briefly during my talk, was because so doing this avoids the problem of that is known as data leakage. And by that I mean including some information of your training set into your test set. So if you normalize your data, taking into account also your training set, well, you have somehow I don't know, falsing the way the network is learning, because the way it is normalized, it also includes information about the training set, and therefore doing that is basically, you know, cheating a little bit on the learning process, because you would end up having maybe higher, better performance than you would actually have on really new unseen data. So if you do it afterwards, then you just keep the method that you use for the normalization. So the normalizer apply node, that's exactly what it does. It just copies which strategy or normalization you've been using. I don't know, for example, zeta score normalization or min max, depending, they are different, and applies it to your test set. So that's the reason why we do it afterwards. Okay, so and then there is another question about whether KNIME has options or capabilities to process video data set. So we have an extension, which is the image processing extension. And that within that extension, you can basically, so we don't have a node that directly, let's say, fragments the video for you into frames, but using the nodes in that extension allows you to fragment each part of the video, and then create the frames for your data set, for example, and then continue with your task. So there is not, like, say, a node called I don't know, fragmenting video node, something like this. But the nodes that you have in there allow you to preprocess your data, so to do your video, for example, and to partition it into frames. Yeah. And then I think there is just one last question about how a data science student entered the field of deep learning. That's a very complicated question, I must say. Probably the hardest one to answer. My suggestion is get your hands dirty with some practice. That's the best way you can start, because so very often working with deep learning is not the most intuitive things to do. There is, depending on which model you're using, on which model you're building, especially when you build complex model, you maybe don't know exactly what's happening. And so to know what's happening, you need to, or to understand what the model is doing, you need to have collect some experience. So start small. That's the first advice is start small and get your hands dirty. So for example, the task that I showed you today, where we built together a demo of a simple, fully connected feed-forward neural network. This is something you could have solved also with a different algorithm, right? You could use, I don't know, maybe a decision tree or I don't know, a random forest, or even simpler. So in this case, maybe it was a little bit of an overkill to use neural network for a task like that. However, the goal was in this case just to show how easy it can be done in KNIME in a codeless way. But if you start using or building such simple networks, it gives you an understanding of what it means to have, for example, a fully connected feed-forward neural network, because you have a dense layer. It helps understand how your layers and how your activation function should be if you have, for example, a multi-class classification problem. So my suggestion is, I know sometimes can be an overkill to use that, but if you really want to get a good understanding to start working with deep learning, start small, build simple neural network for problems that, take the iris dataset, take the Titanic dataset. Those are very simple and easy to access datasets. And try to build your simple model with that first. And then you can go to more complex architecture. So by the time you get there, you've accumulated enough experience, enough understanding of how the process behind this network work, so that it would not be so hard to understand why the model is not learning, why it's not achieving 99% accuracy or 100. And by the way, if that happens, maybe you should be suspicious, because there's nothing. I haven't seen so far. And also Rosaria, which is head of engineering, who has been working in artificial intelligence for more than 25 years. If your model gets 100% accuracy, you should be suspicious about it. There's probably something
wrong.
Something would probably be wrong. So high accuracy, it's okay, but a 100% accuracy should raise some suspicion, some red flags.
Yeah, if you have 100% accuracy and nothing's wrong, you're amazing.
Happens seldom, but yeah.
Yeah. All right. Well, thank you, Roberto, and thank you everyone for joining. My colleagues are telling me that I forgot to mention that if you're interested in learning more about Data Science Dojo, we do have an information session tomorrow at 9 a.m. You can just join on LinkedIn or YouTube. But again, thanks for joining. We'll get that recording out to you as soon as we can, and we'll have the slides attached with that, so you can get all of those links that Roberto is showing at the end of his webinar. And so, yeah, thank you, Roberto, and we hope you have a good evening, I guess, for you.
Yeah.
And everybody else, have a good rest of your day.
Thank you for having me.